given the following recurrent sequences, find the general term and compute their limit. Okay, so by recurrent we mean that this sequence is defined by the previous term. Okay, so the next term is defined by some operation function of the previous terms. Okay. Okay, so the first one is a sub n plus 1 is equal to a sub n plus 1 over 2, starting with 0. Okay, so let's see what the sequence looks like. It started at 0, then 0 plus 1 over 2, 1 over 2, and then 1 over 2 plus 1 is 3 over 2, and then divided by 2 is 3 over 4, and then 3 over 4 plus 1 is 7 over 4, divided by 2 is 7 over 8, and then do the same is 15 over 16, and then 31 over 32, and so on. Okay, and so kind of, you have this kind of tendency trend, right? So if you look at it, the numerator is always one number less than the denominator. So this is 2 minus 1, 4 minus 1, 8 minus 1, 16 minus 1, 32 minus 1. And the denominator are the powers of 2, okay? So this is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, okay? So this is a sub 1, a sub 2. So we could hypothesize that this is going to be 2 to the n, okay? And then the numerator is the same as the denominator minus 1, right? And so it makes sense for 0. So for 0, this is 1 over 1, 0, sorry, so 1 minus 1, 0, okay? Or in other words, you could write this like this, 1 minus 1 over 2n. Sorry, 1 over 2 to the n. Okay, so we need to prove this. Okay, this is kind of a hint or an intuition that we got, but we need to prove this. How do we prove this? Using our old friend induction. Okay, how do we start with induction? We'll start with the first n, in this case n equals 0. Okay, so for a equals 0, we just said this is 1 minus 1 over 2 to the 0, which is 1, and then this is 0. Okay, this is valid. Now assume it's valid for n. Valid for n. Now what happens with n plus 1? Okay, well, let's do a sub n plus 1 is this expression, a sub n plus 1 over 2, and then here in a sub 1 we're going to substitute this, which is our induction hypothesis. Okay, so minus 1, and then sorry, plus 1, and then divided by 2. Okay, so now 1 plus 1 is 2, so we have 2 minus 1 over 2 to the n over 2. And then so if you could put this in the same fraction, this is 2 to the n plus 1 minus 1 over 2 that multiplies 2 to the n, okay? And this is 2 to the n plus 1, which is the same expression as we had, but with n plus 1. So we now know that this expression is valid because we have proven it using induction, okay? And the limit is just making this go to infinity, okay? So the limit of this sequence of a sub n is the limit when n goes to infinity of 1 minus 1 over 2 to the n. Okay, this thing goes to 0 when the limit, so the limit of this is 1. Okay, another way to compute the limit of a recurrent sequence like this is to, okay, so call a the limit of a sub n, which is the same as the limit of a sub n plus 1, okay, because the sequence only has one limit. Okay, so if we take the limit in both sides here, we have a is equal to a plus 1 over 2, okay, and then so this is 2a is equal to a plus 1, which means that a is equal to 1. Okay, so the same result using different methods. Now for second one, b sub n plus 1 is the square root of 2 times b sub n, okay? And you know, before going further, it's maybe easier to transform this to the power version. So this is 2 to the 1/2 times b sub n to the 1/2. Okay, so let's write the terms in b sub n. Okay, so the first one, b sub 0 is 1, and then you have b sub 1 is 2 to the 1/2 times 1, and then you have b sub 2 is 2 to the 1/2 times this to the 1/2, so this is 2 to the 1/4, and then you have 2 to the 1/2 times 2 to the 1/4 times 2 to the 1/8, 2 to the 1/2 times 2 to the 1/4 times 2 to the 1/8 times 2 to the 1/16, and so on and so forth. Okay, and if we start operating with this, we get 2 to the 1/2, 2 to the 3/4, 2 to the 7/8, 2 to the 15/16, and so on. Okay, and if you remember from the previous part, this is actually the numbers in, you can write this as 2 to the 0. These guys are actually the numbers in a sub n. Okay, so you can rewrite b sub n as 2 to the a sub n. Okay, but this is, again, this is an intuition. Okay, so we need to prove this. This is 2 to the 1 minus 1 over 2 to the n. Okay, we have just written that. Okay, so we need to do induction with this. Okay, induction. So for n equals 0, we have b sub 0 is 2 to the 1 minus 1 over 1, so it's 1, 2 to the 0, 1. Okay, so this is valid. This is what we wanted to prove. Now, assuming it's valid for n, what happens with n plus 1? Okay, so b sub n plus 1 is 2 to the 1/2 times b sub n to the 1/2, and b sub n, we're going to use this expression. Okay, so, well, let me erase this because I'm getting out of space. I'm gonna just go this here. Okay, b sub n plus 1 is 2 to the 1/2 times, and then now I'm going with this 2 to the 1 minus 1 over 2 sub n to the 1/2. Okay, and so we can, because this is the same basis, this is 2 to the, and then 1/2 plus 1/2 minus 1 to the 2 n plus 1, and so this is 1, and this is the same as 2 to the 1 minus 1 over 2 to the n plus 1. Okay, so which is the same expression as before, but with n plus 1 instead of n. So the induction hypothesis was true, and so we can write b sub n like this. Okay, and now to find the limit, well, property of the limit is that the limit when n goes to infinity of b sub n is the limit of n goes to infinity of 2 to a sub n, which is 2 to the limit of a sub n 2 to the a, and a was 1, so the limit of this is 2. Okay, and you could also do it the other way around, like before, taking limits here. So the limit when n goes to infinity of this is b, and then this is square root of 2 times b. Okay, so this is b squared is 2 times b, so b squared minus 2b is 0, and then this is b times b minus 2, so either b is 0 or b is 2. But here we know that this will never be 0 because it starts at 1, and then it's multiplied by a number, so it's never going to be 0. And you could again prove it like saying that b sub n is going to be greater than 0 for all n, and again this is proven by induction. So b sub 0 is 1, so it's greater than 0. This is true. Assuming this is true, then b sub n plus 1 is equal to the square root of 2 b sub n, if b sub n is greater than 0, then this is greater than, um, for instance, well, the minimum of b sub n, for instance, but this is greater than 0, okay? Just because it's the product of a positive number, okay? So yeah, proven by induction. So this can, it's not true, and the limit is b equals 2.